Alright, in this video I'm talking about statistical inference, and later I will talk about selective inference, which is the latest achievements in statistics. Modern statistics. So I start by comparing different problems. For example, as you know, this is a design matrix n by p. And P is the feature size, for example, 1 million genes or 100,000 assets. And N is the number of records in your database. And in genetics, we have very few samples, very few number of data in our database, but for self-driving car or AlphaGo, which is a very, very simple problem, N is much larger than P. But in finance, we have big P and big N. Of course, still in finance, the order of P is of order of 100,000 assets, for example. But in genetics, you have order of millions of genes, so it's much more complex. As you know, in statistics, we are interested in inference. We want to say how much we are confident that we are saying, for example, something is true. But in machine learning, they are interested in prediction only. So they use very, very simple algorithms such as deep learning, reinforcement learning, but the problem is here. You know, this one is much more important if you want to grow machine learning beyond its limits. So in statistical inference, we have a population. For example, you have 1 billion data, okay? But we want to sample it because otherwise we cannot control these 1 billion records. How do you want to find the causality, the relationships, and different things? That's why we are interested in sampling distributions and bootstrapping distributions and etc. So in the Bayesian lasso, which is only good for very, very simple problems, and we use Bayesian lasso. So this is the prior and this is the posterior. As you know, posterior is proportional to likelihood multiplied by prior, and that's why and this is the interval for the Bayesian lasso. For example, 10,000 Monte Carlo, Markov chain Monte Carlo for the diabetes problem. In Bootstrap is a new paradigm, and it is invented by Efron in Stanford, I think. Yes, in Stanford. And so this guy is very, very intelligent person for many other things, not just bootstrapping. And his friends, Hasty and Tibshirani, all of them in Stanford. Tibshirani for Lasso. Hasty, I like his PhD thesis because it is non-parametric. And so the bootstrap approach is not a new thing. So it's just think about sampling distribution, but for just one sample, we can create many samples. This is the difference between bootstrap distribution and sampling distribution. So from one sample, so it's just, you want to make sure they make it more accurate. So nothing new, it's just statistics, all the statistics. And for, as you see, one sample, you have many subsamples. So from one sample, we can create a distribution, even from one sample. And this is the magic and interesting things. But there is a difference between cross-validation and Bootstrap. The cross-validation provides estimates of the test error. Bootstrap provides the standard error of the estimates. Cross-validation purpose, or sometimes called cross-validation purpose, is measuring generalization. For example, if you're good in training, are you good in testing as well? The difference between them is the generalization error, and the Bootstrap. So this is the result of Bootstrap. So if you solve your Lasso using Python, for example, you can easily use Bootstrap as well to understand the distributions of these coefficients. These are the coefficients, beta 1 to beta t, coefficients of your Lasso estimator, and some of them are just null and some of them have high values and high intervals. So we can talk about the confidence interval and how confident we are, and etc. But here we are interested in conditioning, because the rest of the methods are very restrictive. They have many assumptions, many restricted assumptions. We cannot do anything in practice. So that's why Professor Robert Tibshirani invented these covariance tests. So this is a covariance test. Covariance test. To understand that if we add another covariate, what happens to the test statistics. So if you want to go through the detail of that, you can see, but the test is just this one. The covariance test is just this one. But the problem is they are not signal variables are not too correlated with noise coefficients. This is the this is the strict assumptions, and that's why we are interested in general methods such as selective inference, sometimes called post-selection inference, because our data says, for example, we don't pick all of the data at once as with the traditional approach. For example, if we have a regression, okay, we only select these data, not these one. Not these one. We select these data because we want to see some contradictions. Because when we select this one, we can do high dimensional inference very, very much easier. So our data lets us select the model. For example, if we condition, that's why it is conditioning in my previous slide. That's why I call it conditioning. Conditioning means that you condition on data. And if you condition on data, you have selected your model based on your conditioning on data. And this is the beauty of that. So a general scheme is just to pick events that you have conditioned. And later I will prove what is A exactly. This is just one exercise in Tibshirani's Lasso book about Lasso. And this is just the ordinary regression. Eta is just the columns of this matrix. So not all of them, just columns of that. Because different columns correspond to different features. And because we want to find the confidence significance of all of these coefficients, we want to do uncertainty analysis. That's why we just pick some of them. And here the population is this. Population, we know the mu, because y, we draw it from a normal distribution of mean mu. Mu is a n by 1 vector, and sigma 2 is like a matrix of covariance, but it's a variance matrix because all of them are 0. We have identically independent samples, and so if we just pick one sample, the next sample is independent of what we have selected in our first draw. And position, so post-selection inference, the idea is very, very straightforward, because if you have, for example, ordinary regression, then everything is crystal clear. But for the lasso problem, you will have to use the KKT condition to understand, to prove the theorem. This is one of the most important theorems in selective inference. And so y, you can decompose it with projection into y and the orthogonal to that. So the theorem says that if you, for example, limit your bound, okay, then you have A, and from that event, so everything, all of these vegas, all of them are just straightforward if we knew that what is B and A. So dependent on A and B, we have this one. Sometimes A and B is better, so we get this one. So all of them are dependent on that. So the one that we are interested is eta transpose y. So we have a bound on that. And the test statistic that we are interested is this one. Is this one. So the result is used to make conditional inference about any linear functional. So our cumulative distribution function, we want to say that null hypothesis is that we draw from uniform distribution. And so we add the next covariate. If we can reject the null hypothesis, we'll repeat this process until adding no other variable can reject the null hypothesis. So this is the normal distribution, but this one is a truncated normal distribution because we have truncated it. For example, in sensor data, we have to use such a model. So in truncated model, the cumulative distribution function, as you see, it is going near uniform probability. Excuse me. I mean, if it is truncated, this one corresponds to this one. And so to prove that, using these KKT conditions, this is the sign of your beta. If it is negative, then if this is negative, then the sign is negative, is -1. S is -1. And to prove that, let's see, to prove that, it's so easy, X transpose E, Y. We want to find beta, okay? So X transpose by plus lambda S of E is equal to X transpose E X E beta, and so beta E is equal to this is the, if we just multiply both sides by this one inverse, you get this. X transpose E, XE minus 1 multiplied by X transpose Y plus lambda SE. So if lambda is equal to 0, it's just same regression, ordinary regression. But now it is not equal to 0, and so we bound on that AY is less than B. For example, if this one is A1, because we bound on this, so this is less than B prime, then AY plus B is less than B prime, so AY is less than, for example, K, and this is our goal, AY is less than it. So you see how straightforward our selection is. So we have selected our data based on our selection. We don't select other points. We are only interested in selecting those points which create some selection under our model. So the data, this is called selective inference. The data selects our model, and then we do the traditional thing, we test the statistics. So as you see, the red line, these red lines are for Lasso. These are for Lasso. And you see, because we have conditioned on some data, it crosses 0. It crosses 0. But otherwise, in ordinary least square, you see, it doesn't cross. Here it doesn't cross. Here it doesn't cross. But the Lasso, if condition on the data, crosses. So that's why the false discovery and correct type 1 error happens. So it shows that condition on some data, some variables such as clue age cannot be significant under response, conditioning on that. And we can implement these selective inference for different paradigms, different algorithms such as least angle regression. This is invented by F1, I think, in 2004, I think, in Stanford. And so least angle regression, less greedy, solve the entire pass problem. And these are the advantages, so pros and cons. And then you see here that the red line indicates the part of the set inside the selection region. So we have used this for different algorithms as this, the same geometric intuition on different algorithm, and the spacing test for LARS. And Adel Javanmard invented new paradigm, but very, very restrictive. So it's very interesting. And you see, this is a geometric intuition. If omega is high dimensional for parameter space, here is just very, very simple low dimensional, but we have to be careful that we don't lose any information when we project it. And this is the flow chart of Adel Javanmard, an Iranian mathematician, and you see it is very, very strong assumption, but it's very beautiful. I really like the geometric intuition of Adel Javanmard. Very genius idea, but maybe not practical for all of the problems, but still it will be developed. Other general tests for high dimensional inference could be found on this article. They defined LOCO, it means leave out covariance inference. For example, we will remove the J's coordinate, condition on the data, this is the data, condition on data as we did, differently. Our